RealtimeSwift will be a SwiftUI style declarative rendering engine for producing real-time video. Today I'm going to show you how I'm composing a rendering pipeline with a syntax like this, and how it generates and diffs view trees that look like this, and an attribute graph like this, and with different source types from a source registry that looks like this. I'm Michael Forrest and I make QCam Presenter, Shoot and Video Pencil, which I'm using to record this video. So how do we take this and turn it into pixel buffers? We need to do a few steps. We need to resolve the view tree. So we need to sort of call that body method and pass through the hierarchy there and get a view tree. We need to diff that against the previous tree. We need to update the persistent graph, which is creating nodes, edges and renderers for newly added views and sort of managing those existing views. We need to track dependencies. So if the sources of those real-time views change, then we need to then re-resolve those views that have changed. And then we need to diff and update the graph and repeat. And I actually, on top of this, I actually have to, render something, which is where we get into pixel buffers, AVFoundation, core image, and core audio. But before we talk about that, let's discuss resolving the view tree. Now, this is something I've been going back and forward on, and I've made a few changes since the last video, and I'm just going to turn that light off. So here is the first thing we do when firing up the RealtimeRenderer the RealtimeViewTree. So we take, when we fire up the renderer, we create this RealtimeViewTree struct that takes the root view and it takes this invalidated IDs binding. Now I'm not doing like state like Swift, so I'm sort of having to use an explicit constructor here. And so then it calls resolve on the root view. So this is, we sort of instantiate this real-time view tree, and then we call resolve on that root view with the root ID and the environment. Resolve is a recursive function that can either resolve the view's body, which is down here. So if it just jumps into the view body and resolves that, calling this same function, or it delegates resolving to the view itself. So views are resolved here. So if it finds a resolvable view, then it calls, resolvable.resolve. So it's taking that view, checking that it's resolvable, and then it calls that inside with observation tracking, so that when this view's dependencies change, then we add the invalidated ID to that binding that was passed in. Now in the host app, we've basically set up a 30 frames a second timer, which is just calling renderer.render, at the application's frame rate, and then it sort of does some render stuff there to actually put it on screen. So in this case, that render calling the host app is just it gets the current drawable from the MTK view and just renders using a CI context that current frame that it's got. But this could be anything like a virtual camera or a video encoder for sending that video over the network, for example. And so back in RealtimeRenderer.render, currently I've got two steps to this. So I'm calling update, and then I'm returning the rendered, core image instance. But I actually saw this handy diagram on WWDC video. I always flub saying WWDC. A couple of days ago, actually, I was watching my phone in bed, and I was like, "Oh, that's useful to know right now." But yeah, they have the first step, they resolve the view, so that's what this is, and then the second step, they actually kind of render that to screen. So I could split that across frames. But and then it's also useful to know that they are kind of calling that from the render loop. So this is why so I am right to wait to do things until this point. I think in this case, if you're running at 30 frames a second, at 60 or 120, then probably this kind of extra frame isn't too much of a problem. But if we're at 30 frames a second, then maybe we just try and do it all in one frame, which is usually the case for a virtual camera. So coming back to, the first thing we called there was real-time, is the update part. So that's sort of the, this part, right, in the SwiftUI render loop. So basically, if we don't have any invalid IDs, then we don't do anything. But if we do, then we are going to check, we're going to, well, basically the current tree has bindings to the invalidated IDs already, so we can just call duplicate resolving invalid views. So it already kind of knows what those bindings are. We don't have to pass that in again. And then here is what that resolving invalid views looks like. So it starts from the root and just recursively checks each child against the invalidated IDs set. So it's got this sort of like nested resolve function sort of inside the view. So it's going like, go into this view. If this is invalid, then first remove it from the list of invalidated IDs. So we are sort of updating state as part of this duplicate resolution thing. And then it calls the same resolve function we just saw before, where it can, have we seen, it calls resolve, which I'll show you in a sec. Did I show you resolve already? I might not have shown you resolve. Yeah, so it shows you this resolve function again, which does the same with observation tracking thing again. I think I need to trust my script. It, and then if it doesn't need to like change it, then it just sort of, it does regenerate the tree, but just from the existing nodes, from the existing view. So it's not like calling that body function again, which might result in lots of stuff happening. So now we can take this new tree and send it back to the graph for reconciliation. So this is the attribute graph, as SwiftUI calls it. I don't know that it's an attribute graph yet. I'm just calling it a persistent nodes and stuff, but we'll get into that in a sec. So we take this new, this next tree, and we reconcile the changes with the current tree before just turning that next tree into the next tree. So let's have a look at reconcile changes. So this is where it gets big. So RealtimeGraph is a class type owned by the RealtimeRenderer, so owned by that renderer class, and there's just one of them, and it has dictionaries of nodes and edges, all keyed on that real-time identity struct. Edges basically represent directional connections between nodes. So we have like node, 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 and then an edge is just a line from a node to a node. So you can sort of imagine that we can have these nodes, but then there might be one up here that's, it's feasible that two different nodes could be pointing to the same one. So that's when it becomes a graph rather than just a normal kind of hierarchy. In this so we're sort of trying to get away from recursion a bit as well here, which, by the way, if you want to know why recursion is a problem, then this video by Nick Barker is definitely worth a look. Recursion explained. But yeah, this is so what we're actually doing here. So first we're taking a diff. We're diffing those two view trees to find out. To find out what happened before and after that hierarchy changed. So that then gives us a flat list of identifiers and whether they were added, removed, or updated. So here's how I'm doing the delta. We can see we've just got our own stack here. So this is how we're avoiding the normal recursion. So instead of using the system stack, which can sort of like overflow, we're just using our own sort of custom made stack, and just we just keep pushing child views onto that stack and in this while loop until there's nothing left, and it's adding the children. You see, so this stack is sort of like adding children as it goes through. But the important thing here is that we're how we're kind of checking for what's happened, right? So the bad thing I'm doing here is probably that to check for an update. So if we know we're updated, I'm literally just comparing the debug description because which is not ideal. It currently relies on the fact that I've added custom debug description properties to all of the types I care about, so that pertinent information is kind of in the string. But I need a more robust equality test that doesn't do a load of string comparisons, but that does give us our updates. And then other than that, we're adding stuff that's new, we're adding stuff that's removed, and that's all keyed on IDs. But basically this more or less came fully formed out of ChatGPT. So, it's a bit loose for my liking, and the names aren't great, but like it's, it does the job. It gets me the diffs that I need. So once we've got the changes, we can update the graph, right? So what does that mean, right? So anything that's added gets, well, first it gets, well, the upsert, as you can imagine, like if the node already exists, it just leaves it. But if it's a new one, then it adds it. And then it makes sure that it's, and this add edge is idempotent. So if you add it twice, it's just a set, so it won't kind of add duplicates in there. But it sort of has to find the parent node through this next tree.find parent node ID, but which I don't know how I feel about that, but that's kind of how I can sort of make sure that the graph is correct. And then removed nodes get marked as exiting, right? So if it finds a node that's not there anymore, then it's marked for exit. And this is probably, for me, the most important detail, because we want to be able to instantly update the underlying view and let the framework handle gracefully removing unused renderers with animation and stuff. So there's two things here. Like, we can't just, if I just use the flat tree, then I've got no way of transitioning. And I've also, like, the fact that it still exists in the graph, even though it's in a removed state, means I can still traverse the graph and find it and do whatever I need to do with it until it's ready to be removed. So this is really what that graph is all about as well. So, if something has changed, we set it to updating, and I replace the resolved view with the latest one, so it knows what it's supposed to look like now and can manage that transition. So what is a persistent node? Basically, this is a class type, so these kind of stay in those sets. It's owned by the graph, and it has its own copy of that resolved view struct. And by the way, that resolved view is essentially a way of associating an identity that we kind of figure out from the position of the nodes with a real-time view and a current and an environment value, a set of environment values as they currently are at this point in the hierarchy, and then any children. So this is how the tree works, right? Through these resolved view children, that's how we get that tree hierarchy. So then, if we change that resolved view, it's going to call update, or if we change the phase to entering or exiting, then it does a stop. And these are kind of like rough and ready things for now. And then down here we can see how it makes renderers. So if it's a leaf or a container, then it gets a renderer, and the renderer, the renderer is going to belong to a specific view type, right? So a text layer in its make renderer call creates a TextLayerNode with the text that it got from the leaf, from the text layer, right? And these names are going to improve, by the way. Like renderer is, these need to be called something renderer. And then the TextLayerNode is a renderer type, which currently does this like attributed string rendering stuff to just turn that into something that we can put on screen as a core image. So it's really quick and dirty for now. But you can see up here, like I'll show you. Here's another view, RealtimeSource view, which I'm going to be using a lot. This makes a RealtimeSource render node from the source if it can find it in the registry, which is keyed on the source name, right? So this is how we're kind of creating that. And then this is now a node that can sort of like ask for frames and do the correct thing to create the right image. Here's what that renderer protocol looks like for now. So at the moment it's got like start, stop, render image, and update to give it a new view, and then I've just given it some default start and stops. I really wanted to make the stuff have an associated type, but it was a bit of a bloodbath because it all propagates back up to that resolved view, which takes an any real-time view, which, I've been watching, it's just like, you just get like loads of errors. I'm just trying to figure out how to do it and getting a headache. And, I've been watching more videos on Swift generics and wondering about protocol witnesses, but for now I'm settling for these box types and guard clauses, basically. So in the text one, it just checks that it's the right kind of node, and if it's not, then it just gives up. So I don't love that. I tried to figure it out this morning and spent another hour on it, but I couldn't quite figure it out. But we'll get there. Maybe someone out there can help. But yeah, back to RealtimeRenderer.update. We've diffed, we've diffed and resolved And so all of our graph is up to date with all the right renderers and with all the right view state attached to them. And it's time to render it. So we can call render. So in our render function, we can now call render node and just like return that, whatever the result of that. So we've got a little sketchy. I'm just thinking that's probably not necessarily guaranteed to work, because we might, I don't know what might happen there. But anyway, this is still work in progress. So in render node, I'm just doing a bit of recursion and doing some quick and dirty compositing, like next composited over, all this kind of stuff, just to kind of put something together that we can put on screen. And then just to mention, the renderers get this start async and stop async along with rendering image. So I'm planning on giving this an optional core audio callback as well, so that the renderers can also provide audio. So that will be like a convention C type thing that can just be called as a C function, in the way that certain frameworks just want to do that, and I think that's going to be really good for audio. And then just so you can see, like, I just added this movie player source yesterday, so it's it's a very minimal version of a video player, which what does it do? It basically makes makes an asset from the URL you give it, and makes a player item and a player, and sort of saves the default transform, which I've found myself needing when vertical videos were recorded on a phone. But yeah, and then this start function just, sets up the player, adds this video output thing and just plays it. So now that's just like playing. Actually, like sound is coming out at the moment, and which I don't really want. And then the rendering part, when image is called, it's gonna sort of try and get a new pixel buffer. So this is this video output thing that you get with AVKit that just lets you get frames from AV players. And so then if it gets one, then it just wraps that in a core image and transforms it by the preferred transform. And then we just like return whatever the last image we had was, so that we don't get any weird flickering and stuff. So that's how that's returning. The video player is going to return videos for this test. And then just to look at how the camera source works. So instead of the camera source is, instead of making images in response to pulls from the framework, it's driven by AV capture session. So whenever like a frame comes, then it's just going to like make a copy of it in core image and like kind of keep that in image, and then that's what the framework is getting. So this version is probably doing more work than it needs to for now, but like that's how that's working. But anyway, I think that is most of where I'm up to. So let's have a quick demo. I hope you don't mind this video being a little bit loose. I want to do just a one take thing, and not sort of get bogged down too much in these devlogs. So it's not going to be a slick production. But let's go to the demo and see what we get. Get ready to feel underwhelmed. Right. So here is let's just reset zoom. Can I just I just want to be zoomed out here. So what I'm going to show, this might be a bit hard to see, but this is running. So I've actually got some debugging stuff down here. So down here you can see this is the current render tree, and then this is the attribute graph. Like this is the current graph. So we can sort of like zoom in and see that I am currently showing USB video and some text. So you should be able to see the text up here. So I'm showing USB video and some text, and then the nodes that we get here are, we've got this kind of source registry at the top. There's a Z stack, which probably shouldn't be saying, well, it hasn't updated since it was added, so it doesn't need to do it. It's just showing entering still. And then the clock, you can see that ticking away, and then the USB video has only been added, and then that sort of like maps over, to the stuff that is to the stuff over here. I'm just going to zoom out and save this slightly zoomed out zoom level as my default zoom for this card. Right. So what I can do now is I can make. So what I've got here is if presentation timestamp, percent. If it's every 5 seconds, it's going to toggle this view on and off. So if we add this view, then now we're going to get, this is obviously like now it's a new application. So now you can see we've got this optional real-time source view, and then, and then every 5 seconds, my FaceTime camera, so this is my worst camera on my computer, getting fired up and layered on top, and then the text just sort of sits on the top of everything. So this is, you can see that it's freezing when it adds the video, because currently that whole start operation, which starts the capture session, is happening on the main thread, so we are getting a stutter, and that's something that I need to have a good think about how I want to prepare content, so that, because basically I want the snappiest possible transitions when you're navigating through QCam Presenter, which is what this is all kind of being used for. And that means thinking seriously, like finding the bottlenecks, which I know where they are. It's just figuring out how to find the perfect balance of responsiveness and like not firing up 67 different cameras at once and like playing all the videos in the background or whatever. So this is something that's going to be a lot easier to manage now that I've got my little attribute graph. So you can see down here, we are, if I kind of like zoom in down here, I'll show you, can sort of see what's happening when it's adding and removing the stuff. So we've got our Z stack, and then we've got our optional, and we've got this FaceTime camera. So it's entering, and so it's entered, right? And then it gets marked as gone. So now it's exiting, and then meanwhile this is updating, and so we can see. And then this is just kind of like stable. So this is just like drawing the frames as it needs them. So finally, if I just like reset the zoom on that, I'll just show you. I've also, so by the way, so just so you know where USB video is coming from, inside here we're going environment appstate.source registry. So that if we click into there, we can see that I've just registered all the attached cameras into the source registry, making camera sources for them. But then I've also like loaded in a little video and added movie source with the name Harvey. So now when I turn this on, we're going to get rebuilds the app, and then now we can see that there's that video playing on top of everything. That is basically a little demo of where I'm up to. It's been very challenging working on this the last few days, but and finding time to do it as well whilst also running a business. But I'm really glad that I've got it to the state where I'm putting stuff on screen. I have my hooks for starting and stopping those video sources. And the next thing is going to be, I do want to sort of like get audio in there sooner rather than later, but then it's view modifiers, layout engine, that kind of stuff. Chris Eidoff, I will be looking at his stuff in a lot of detail to find out, how, just to really understand how all that works. But to be honest, there's a ring in this room which I don't like, but I'm just living with it for this video. When it comes to sort of like laying out, sort of having an H stacks and V stacks and X's and Y's and rects and all that kind of stuff, this is stuff I was doing in like 2005, in Flash. I was doing like these frameworks for building up, like laying out views and doing all this kind of stuff, and the padding and the videos and the text and measuring text and laying all that stuff out. So I'm sort of like, now that I've got this framework kind of like letting me specify stuff in a Swift UI style, then I can start focusing on that stuff that I'm a lot more comfortable with. 20 years I've been like laying out graphics on different platforms, so I'm hoping that I can get a good bit of pace now that I've sort of figured out all this stuff with the generics and the attribute graphs and the view hierarchies and all that kind of stuff. So yes, so thank you for watching, I guess is all I say. So something I always like to show at the end of these videos is that we just show you like how the sausage is made, like how I'm going to break the fourth wall and kind of show you like the script that I used. I wish it hadn't gone onto the other screen, but this is like the tool I'm using. And so here's the video that I've just gone through. So you can see like there's a lot of I've done a one take recording, but I spent like an hour and a half kind of like pulling together all these screenshots. And you say we've got this sort of like ability to sort of bring in really quickly, paste in screenshots, really quickly put a title on, put some little icons on. And so I just like screenshotted all the different things. I've got my bullet points, transitions. So this is just all so that when I present it, I can just press play. And then like my rig is like, I've got, let's pull this up a bit. You see, I've got a teleprompter up here. I've got my iPad where I can draw. Sorry, I'll show you. So it's a very old phone that I'm using here. So my iPad lets me kind of draw on stuff on the screen. And then, yeah, I've got my microphone and the camera is behind the teleprompter. So if you're interested in the app that this is all going to, that's called QCam Presenter. The iPad app is called Video Pencil. It also lets you go like that. You can go to qcam.app/download and give that a try. Thank you for watching this. If you're interested, there's probably a discussion on Reddit. Every other video I upload about this seems to get a bit of attention on there. So I'm sort of learning from people on there. So I'm really like, I don't know all the answers, honestly. I'm figuring this out as I go. I have been deep into kind of AVFoundation and stuff the last 2 or 3 years, really like understanding all the different stuff there. So I'm sort of able to come to this with a fairly crisp understanding of what needs to be done to get video on screen, and what is the life cycle of a CM sample buffer from a camera. Like I'm pretty intimate with all that stuff, but now I'm just trying to like reconcile all that knowledge into something that can become a framework and potentially be open sourced. Depends if I can get people, it depends who's interested, because it is a bit of work to kind of start a community project like that. But either way, I'm hoping it's just going to massively improve the quality of the video output from QCam, because it's going to make it a lot easier to think about and reason about once we've got this declarative style renderer. So thank you so much for watching, and subscribe to see the next one. And there's a Discord as well if you want to find that as well. See you, bye!